Well, let me welcome everyone today to our next premise plumbing modeling webinar. Thanks to everyone who's been participating with us throughout this whole last year. Today, the topic of our presentations is about the design of premise plumbing systems. So again, today our title is called Toward the Use of Hydraulic Models for Designing Premise Plumbing Systems and Informing Codes and Standards. And next slide, please, Bill. We've talked a lot in our webinar series so far about lots of different aspects of hydraulic and water quality modeling of premise plumbing systems. So just a reminder on this slide here that a lot of the motivation for this is to really investigate the human health concerns that we have from premise plumbing contaminants. So we might use these types of models to look at lots of different things, including the persistence, fate, and transport of contaminants in buildings, understanding the roles of fixtures and plumbing materials, and creating conditions that could lead to poor water quality and human exposure to contaminants. Looking at how we might manage our premise plumbing systems better to try to reduce those risks. And then looking also at how we could try to remove the contaminants from the system by using flushing or other methods. So these are kind of some of the motivations that we've talked about for wanting to use hydraulic and water quality models of premise plumbing and to develop them, which is what we've been focused on in this series. So today the topic is really, can we use these types of hydraulic models to help design premise plumbing systems and to inform codes and standards, and really to also be looking in the future, how might we want to design premise plumbing systems differently in the future if we're thinking about things like climate change or changes in population or changes in water use or other examples. So that's really kind of where we're going toward today, but we're really going to focus on what it means to design a premise plumbing system today and how we do it today. So next slide, please, Bill. So again, today the focus is really on how do you design a premise plumbing layout. And there's many software tools that are available, and you're going to hear from several different speakers. They all use different approaches. And so one of the really interesting things today is to really learn how these approaches are different. What are the different codes and standards that are informing those approaches? And what are the different intentions behind the designs and the different assumptions that will all lead to very different designs and layouts of premise plumbing systems. Many of these approaches are based on design factors like peak flows, and so we're going to be hearing a lot about that today. This picture here shows an image from Bentley's Open Building Designer tool, and you can see the nice 3D layout of the plumbing system. Next slide, please. So the methods we're going to be talking about today involve a lot of different calculations, and this slide, Tom Walski shared with me this information, so I'm happy to share it with you guys today. But basically, it helps explain what the inputs are to these types of calculations and modeling and what the outputs are. So here you see a lot of information about what is the layout and the connectivity of your pipe system. What types of fixtures are you going to have? And fixture units is something we're going to hear a lot about today, which is a design factor that is used when we're designing these premise plumbing systems. We also use inputs about the pipe materials, the diameters of the pipes, the available lengths of pipes, the pressure and the target velocity, the elevation of all the different components. And then the outputs of these methods are things like the flow in the system, the diameter of the pipes that you're selecting, the actual velocity and head loss, and hydraulic grade and pressure that you'll achieve. So again, here are some nice figures of some different design software. And next slide, please. So we talk about modeling when we're designing a building and designing the premise plumbing system, but we also talk about hydraulic modeling. So this slide is just to really help clarify that we're talking about two different kinds of modeling. So primarily throughout this webinar series, we've been talking about hydraulic modeling, where you might use something like EPANet, and in that kind of modeling, which is described in the bottom of the slide here, the basic premise is that you're conserving mass at each junction, and you're modeling either under steady or dynamic conditions, and you're determining the actual velocities, pressures, and maybe the concentration of some substance in the water over time. In contrast, when we talk about the pipe sizing modeling, which we're going to be talking about today, that's a different kind of a modeling where we're doing some calculations that are conserving what we're calling fixture values at each junction, each segment in the pipes. And so the fixture values are conserved, and the fixture values are design factors, again, that are based on flow rates, but they're not exactly flow rates. They assume that not all fixtures are in use at one time. And again, you'll hear a little bit more about that from several of the speakers today. So again, just to clarify that we're going to be using modeling in different ways today than we might have in the past. Next slide, Bill. So the way the webinar is going to work today is Jeremy Williams is going to speak next, and he's going to give you an overview of how this design process works from a practitioner who does this a lot. Then we're going to talk about some of the different approaches to the pipe sizing methods. So Dan Cole is going to start, and he's going to explain the approaches that we use in the US, including one approach that uses a water demand calculator. And then we have Miriam Blocker from the Netherlands, who's going to talk about how the design approach is different in the Netherlands, and Frank Schmidt, who will talk about design approaches in Germany. And then Gary Klein is going to give us a presentation about how architectural, not engineering decisions, but architectural decisions can also impact premise plumbing systems. Then what we're going to do is basically have a panel discussion where all of them will be on board with us. We'll talk about actually what we're going to do. I'll tell you in the next couple of slides exactly what we're going to do, but we're going to have a panel discussion where we talk about the differences in these approaches and what the implications are for premise plumbing. And then Bill Platten is going to wrap us up at the end by talking about what the implications are then for hydraulic modeling in the future and how it could be used to help with these processes. Next slide. So one thing that's fun today is that we're basically using this figure that you see here on this slide, which is a single apartment building. And we're going to be talking, each of the different participants in this webinar is going to be talking about this same design, so the same layout for the premise plumbing in this single apartment. And they're going to talk about how the different design standards that they use and design assumptions can lead to very different pipe sizes and flows and residence time and water quality. So because we're going to see this slide, this figure a lot through the presentation, I thought I would just start with it right now to make sure we're all familiar with it. So basically, this is a single apartment in a 45-unit building. And on the next slide, I'll show you what that whole apartment building looks like. But just to focus on the premise plumbing, so this particular apartment has a kitchen that you can see at the top right with a sink and a dishwasher. It also has a bathroom in the middle there, which has a shower and a tub combo, a toilet and a sink. And then it also has a master bathroom with a shower, a toilet, and 2 sinks. And then a utility room at the bottom left corner, which includes the washing machine, the sink, a sink, and a hot water heater. So we're going to be talking a lot about this, so just want to make sure you're familiar with it as we go through. Next slide, Bill. Great, and this shows you a single floor here of the entire apartment building. So you can see there's 5 apartments at the top, and then there's 4 on the other side, the bottom side, with it looks like, you know, some elevators taking up the room of the other apartment. So there's 9 apartments on each floor, and there's 5 floors in the apartment building. So these are the designs that we're going to be talking about throughout all the presentations today. So you'll hear a lot more about it. All right, so with that, let's just jump right in, and I will turn it over to Jeremy Williams to give a presentation about the design approach.
Good morning, everybody. Thank you for joining us in this presentation. So I'm here to summarize the basic design process. So I'm keeping this high level. It's not meant to be exhaustive and go through the complete design, but just kind of how we approach design from the high level and using the model that that Regan showed as we go through the process. So this is the plan view layout, which is a top-down view of the apartment by itself. And then off to the right here, we have what we call a 3D isometric. It just shows it a little bit better to illustrate what goes on. So like she said, we have a kitchen sink with a dishwasher. The bathroom sink can be termed as a lavatory as we go through this. So I want to get some of those in there. Toilet, which is also known as a water closet, the tub with shower, and a shower. I omitted the laundry area just for clarity in this, but it's equally as important to consider in the design. So once we lay out the fixtures, we start to plan the mains. We try to get the mains as close to the fixtures as possible, so there's the least amount of time from the main to the fixture for hot water purposes mostly, but for residence time. As we go through this, you'll learn a little bit about residence time. So we start with the mains. We have the cold water coming from the hallway that's in here, so that's starting at this pipe here. From there, we go to place the water heater. So the water heater being in the back corner of this utility laundry space. And then we connect the branch piping between the main and the fixture. So with this, we have a complete connected system. The fixtures actually have the fixture unit values or the GPM values, depending on what method you use, to inform the pipe of what's connected to it. So once everything's connected, the pipe has, the values that go through it. With fixture units, it uses the diversities factors. So, the flow of the kitchen sink doesn't get added to the flow of these two fixtures and so on. So it comes out to a GPM. We use velocity method in this instance. And for cold water, we use 8 feet per second on a copper pipe to size the piping with no diversity factor outside of the normal Hunter's curve, as we've ventured into as we've gone through this. So with this in the US, and Frank will get a little bit more detail of what they do in Germany, but in the US, we would do this typical layout and tell the builder to build this 45 times. So we're not going to go through and detail size every single room, which they can vary based on the pressure. So the further away from the source you get, the lower the pressure is, so the bigger your pipe has to be to overcome that pressure loss. But like I said, in the US, we just tell the builder to build this 45 times, and we would put this on a drawing and be done with it. So from there, we zoom out to look at the whole apartment building. I got like a little clip of what we have in the apartment here. I show this, branch line, which is the piping that goes out to the hallway. So we take the known supply from the typical apartment. That's got a fixed size, and then we take that one, and then we add the second, third, fourth, and fifth apartments on the one side of the hallway, and we add the other 4 on the other side of the hallway to get 9 total apartments. So all these have a fixture unit value or GPM value that we have assigned to it and use it to size the floor. So once we got the branches, we run a main through the middle of the corridor to connect all the branches, and then we have this main connector to the riser that's coming in that central area by the elevators in the lobby. With it all connected, the model is telling us what the GPMs or fixture units are of each pipe. We can go through the process of sizing the floor by itself and can get the sizes and values kicked out to tell the builder what they need to build on the floor itself. So once we size one floor, the rest of the floors are assumed to be identical. We size the 5th floor first because it's the worst case scenario, and all the floors below will be better than the 5th floor, but the same size, just to keep it simple. So we go from the 5th floor down to the 4th floor. We have the 3rd floor, 2nd floor, and then 1st. And then all those floors need to get tied together in the middle here with a riser. So I'm going to zoom in to the riser area. So we connect each floor with a common vertical pipe throughout the building. Incoming water supply is coming in down below, so that's from your municipality or your street. And then we size finally the riser going through. So that gives us our final size at the incoming water supply area that we're going to be talking about later. And then you just add water. Thank you.
Great. Our next presenter then is Dan Cole from IAPMO.
All right, I think we're ready to go. I was asked to do a presentation on pipe sizing, and this is how I started. And I thought this would be a very interesting topic to explain the different types of pipes and so forth. But I was told I was starting on the wrong path, on the wrong topic, and they said no, it's premise plumbing pipe size method. So that's what we're going to talk about, and the pipe sizing method that's used in the U.S. And in the U.S., there are 3 model codes, and we call these codes in the U.S. versus standards. We call these plumbing codes. However, there's only one code, the UPC, which is an American National Standard, which is governed by the American National Standards Institute. The other 2 codes here are not American National Standards. The Uniform Plumbing Code and the International Plumbing Code, those are the 2 most widely used model codes in the United States. The National Standard Plumbing Code is used primarily in one state, New Jersey, and in some jurisdictions in Maryland. So very limited use in the United States, but there is still a state that adopts the National Standard Plumbing Code. So the universal method in all of those model codes, the universal method used for premise plumbing pipe sizing is known as the fixture unit method, developed by Dr. Roy Hunter in 1940s, actually in the 1930s, but he published his document in 1940. And what we see here on the left-hand side, this is actually the design curve, and it's known as Hunter's curve. And that is derived from plotting discrete values of the 99th percentile of the probable relation of busy fixtures to the total number of fixtures. And he designed this using 3 types of plumbing fixtures: a tank type toilet, a flushometer valve toilet, and a bathtub. Those were the most commonly used fixtures at that time. So he actually had 3 design curves, and his intent was he wanted to have one design curve for all building types. And so he weighted the 3 fixtures using a scale of 10. The flushometer valve curve was given a value of 10, and the other 2 curves were weighted relative to that flushometer valve curve. And when he weighted these curves, the curves actually collapsed toward the flushometer valve curve. You see that there's 2 design curves on the low end, one for flush tank curves and one for flushometer valve curves. The reason being is that the flush tank curve, there was still a significant difference once the curves collapsed toward the flush valve curve. There was still a significant difference between the flush tank and the flush valve curve. So he kept those separate until they intersected at around 1,000 fixture units, where the curve then becomes a common design curve. So that is the design curve that's still used today. Alongside the design curve, there is this table where you have in one column a list of plumbing fixtures, and then you have a distinction between public use occupancy and private use occupancy. And the fixture values are less in the private use occupancies than a public use because the frequency of fixture use was not as frequent in a private use, and that's why these fixture unit values are less. So basically, what you would do for pipe sizing purposes, you would just add up the total number of fixture units in that building, and once you have the total value, you would use the x-axis, which is the fixture units, and then you would follow that, whatever that number is, you would just follow that x-axis till it intersects one of the curves, whether the system is predominantly a flush tank system or a flush valve system. You would just rise vertically till you intersect the curve, and then you would move over to the y-axis, and that would give your estimated demand for that number of fixture unit values. I can't, if you really want to go into detail on how that curve was designed and what the engineering assumptions were that Roy Hunter used, this is the document to go to. It's still published by the American Society of Plumbing Engineers. And this goes into great detail by Roy Hunter on how the design curve was actually created, the binomial model that he used, how he weighted the curves, how he combined the curves, how he derived the fixture unit values. All of this is in great detail in this document. So this would be a great source to go to if you really wanted to do a deeper dive into that design curve. Well, that was in 1940. The only advances made in the plumbing codes was the expansion of the fixture table and also the fixture unit values. And the fixture unit values have been modified over the years. Now, here's an example of the fixture unit tables in the Uniform Plumbing Code and the International Plumbing Code. And they have developed the fixture unit values differently through the years. For example, you can see the difference in fixture unit value just for a bathtub between the two codes, UPC 4 fixture units versus the IPC 1.4 fixture units. Same thing with the shower. There's a difference in fixture unit values in a shower. And these are just some examples where there are differences in fixture unit values between the codes. However, the design curve has never been modified. These fixture unit values still get applied to the design curve that we saw earlier. And this is the National Standard Plumbing Code. And the unique feature of the National Standard Plumbing Code is that one table, they have used groupings instead of individual fixture units. So you have a bathroom groups and a fixture unit value applied to a bathroom group rather than the individual fixtures within that bathroom group. And at the very bottom, you see a kitchen group and you see a laundry group where the fixtures are grouped together, and as a grouping, they're assigned a single fixture unit value. They also have another table that does show the individual fixtures with individual fixture unit values. So again, the three codes still are using the fixture unit method. They are still using the same design curve, Hunter's curve. However, they are modifying the fixture unit values differently between the three codes. Now, what IATMO has done in recent years, and first time published in the 2018 Uniform Plumbing Code, is a new statistical model to estimate peak demand. And we call this the water demand calculator. And this replaces the fixture unit method that we just saw for estimating peak demand. There are no fixture unit tables. That's not needed, nor is there a design curve. The only input, actually, this is moving Hunter into the 21st century and using a spreadsheet rather than plotting things on a graph. So the only input needed is the number of fixtures, which would be in this column here. You would input the number of fixtures, and seeing our model that Jeremy put forth, this is a 45 unit apartment, and we are going to size the incoming water service for all 45 units. So we would put the total number of fixtures in this column. And then you would just click Run Water Demand Calculator, and the output information is on the right-hand side. You have the total number of fixtures. You have the peak demand estimate at the 99th percentile, and here it's 30.7 gallons per minute. You have a Hunter number, which is a dimensionless number. I don't have time right now to really get into what this number represents. It's just the expected value. You have a stagnation probability, and because of the large number of plumbing fixtures, the stagnation probability is approaching 0%. So this is the first time since the 1940s that a plumbing code has ever put something forward to revise that design curve. So this brings the design curve into the current century. You see these flow rates are very conservative. These are water conserving flow rates for water conserving plumbing fixtures. That was intentional in this design. And everything in the white boxes can be modified. The only thing is that these flow rates cannot exceed the maximum recommended flow rates in this blue column here. You can go lower. You can use less flow rate fixtures, but this is really for water conserving plumbing fixtures. So here is another example of the water demand calculator, and this is for sizing of 1 unit. So you have a 45 unit apartment and you want to estimate the design flow rate for just 1 apartment. And so these are the number of fixtures that you would put in for the 1 apartment. And again, the output is in the right-hand side. And here you only have 11 fixtures. The peak demand flow rate is estimated at 9 gallons per minute. So again, you're not using fixture unit values. You're only inputting the number of fixtures. You don't have a design curve. This will give you the peak design flow rate directly on the right-hand side. But this only estimates the peak demand. This doesn't tell you how to get from this point to calculate the actual pipe size diameter required for any riser, branch, or incoming building supply. So each plumbing code also has procedures, and they're common procedures. And one of the procedures that is needed is to calculate the permissible friction loss. And what you're trying to calculate is the friction loss per 100 feet of pipe. And that's because you're going to be using a nomograph, and a nomograph is built on friction loss per 100 feet of pipe. So you're identifying the type of material, what nomograph you're going to use based on your type of material. And this is just an example of some of the friction losses that you need to look at. There may be others, but this is like an example, the available pressure at the meter. What is the minimum residual pressure that you will need in your plumbing system? And this will vary depending on the type of fixtures you have and what that residual pressure is needed at, minimum residual pressure. Head loss, especially if you have multi-story buildings, you're going to have to factor in your head loss. And then you calculate your available pressure for friction loss. And then you calculate your developed length, your longest length of run of pipe. And then you have to allot for your fixture or your fitting allowance, the friction loss through fittings. And this is something that Gary Klein is researching currently right now, is re-evaluating friction loss tables for plumbing fittings. And then you have your total developed length of pipe, and then you just use a simple mathematic calculation. You take your 21.1 PSI and you divide that by your 141, your length, and then you multiply it by 100 to get your permissible friction loss per 100 feet of pipe. In this case, is 15 PSI. You take this information, and this is the nomograph that each plumbing code publishes. And there's a number of these nomographs depending on the pipe material being used. And this is just one example of copper tubing type M, L, and K. And in this nomograph, you have the friction loss per 100 feet of pipe on the x-axis. You have your flow rate. And this is where the water demand calculator, or if you're using Hunter's curve, the fixture unit method, the peak demand estimate will use the y-axis in this on the right-hand side. And interior, you have diagonals, and you have your upper to lower diagonals, which is your velocity diagonals, and then your right to left diagonals are your pipe sizing. So in the example that I used before, at 15 PSI, you would start here and you would draw a vertical line to your velocity limitation. And for cold water, for copper pipe material, the velocity limitation is 8 feet per second. So you would run your vertical line till it intersects the velocity diagonal. And then you could run your pipe sizing to the peak flow rate that pipe size is allowed for. So for example, your one inch size pipe at 8 feet per second, the maximum flow rate allowable in that 1 inch of pipe is 20 gallons per minute. And for your hot water, for copper piping, the velocity limitation is 5 feet per second. So you would run your vertical line from your 15 PSI till it intersects the velocity of 5 feet per second. And then you would run your horizontals over from your pipe diameter to the flow rate, and that will give you your maximum flow rate. So the nomograph uses these 4 parameters to select the proper pipe diameter: your friction loss in PSI per 100 feet of pipe, your flow rate in GPM, your velocity in feet per second, and that will get you to your proper pipe diameter. So whether you're using the Hunter's curve and the fixture unit method, or whether you're using the water supply or the water demand calculator, you are still using this nomograph to derive your proper sizing for the pipe diameter.
Thank you so much, Dan. Our next speaker is Miriam Blocker from KWR Water Research Institute.
So you might recognize this first slide, but I altered it a little bit. Thanks to Dan. Dan made a terrific presentation, and I decided to just use it, but adapt it a little bit towards the Netherlands. So I also put up some Dutch pipes just for fun with the Dutch flag and the Delft blue there. But otherwise, I've been also using Dan's presentation, and I don't need to go into all the details. You've heard already quite a lot. And of course, in the Netherlands, it's not completely different. I mean, there are quite some similarities. So I'm not going to go into all the details again. So I'm showing you how we have been designing this same building in the Netherlands, or how we would. And here I really have to tell you that I didn't do that specific sizing work, but Henk-Jan Reineveld from Hogendoorn Sanitair Installatie, he's the one who did that. So thank you very much, Henk-Jan. And we decided to only do the apartment building and not inside the apartment. So some of the Dutch figures there are missing, just because we wanted to save ourselves a little bit of time, not because we couldn't do it. We also have a few design codes. On the left, you can see ISO 30, and that's really focused on drinking water installations inside houses or apartments, but really inside the apartment. And it uses sort of a fixture unit method. Then there is the ISO 55, and that's for apartment buildings and non-residential buildings. And the one in the middle is the old one, which uses a variation of the fixture unit method. And the new one from 2013 that uses a method that is based on SIMDEUM, so based on stochastic demand models. So the fixture unit method in the Netherlands, I think originally, but it's hard to find the real true reference, is something from Germany in the 1940s. It is also known as the Q square root N method, where Q is a certain value of flow in liters per second. And then N is the number of fixture units or the number of apartments if you go to an apartment building. So a toilet is typically a quarter of a fixture unit, a kitchen tap, bathroom tap is 1, and a washing machine and a dishwasher would be 4. So you first convert all the flow rates, maximum flow rates for each tap to a fixture unit, and then you add those, and that's the number of fixture units for your apartment. And then the maximum flow from that is that Q square root N that would then account for the chances of simultaneous use. And the same would go, and that was where we probably went horribly wrong, or we believe, because we didn't have anything else. Let's just not just use it inside the apartment, but also outside. So in an apartment building, also in the streets, this method has been using and been overestimating grossly the maximum flows. But this was the old method. So, and for our American public, on the left, I've used the American units, so gallons per minute, and on the right is liters per second. That personally I'm a little bit more comfortable with. Now, as we did do some measurements of actual flows occurring in streets and apartment buildings, we found that this Q square root N method was overestimating quite a bit. And we decided to develop a new method, and that is based on how many people are there and how likely is it that they use water. And we developed SIMDEUM. I've talked about it before. So in some of the previous webinars, you can see that. What we did is for apartment buildings and also for offices and hotels, calculate maximum flows per day and per year, and then change the number of apartments or the number of employees in an office or the number of rooms in a hotel, and then go slowly from 0 to a lot. And we found that we could describe this curve that was appearing as something like Q1 plus Q2 times the square root of N, where N would then be the number of apartments, for example, plus Q3 times N. And this Q3 is rather small, but it will be you will see that there is a straight line when n is large, and in this middle part there's still this square root curve that you can see appearing. We also have made this available not just as this very horrible equation, but also in a spreadsheet. And the nice thing here is that you can also mix different types of apartments in a building. So you can say it's 45 of this specific type, but it could also be 20 smaller ones, a studio with just one person living and very simple, and a few really luxury apartments in there, etc. So depending on the luxury versus more simple, the number of people, and if people would be mainly working from home or being at home or being away, those are the characteristics of those types of apartments. And the result there is your maximum flow rate, your maximum momentary flow for cold and hot water. And it also gives you a maximum water volume in various time steps, and that will help you to then design your hot water boiler. So there is actually more information that we have from this type of approach than we had with the fixture unit, which only gives us maximum flow rate for cold water, basically. Of course, we also have these nomograms and things like that, but built into software, it makes it a lot easier. And again, of course, you give in pipe lengths, flow rates, and pressure at the street level, and then some criteria as minimal pressure at the end or maximum pressure drop, maximum flow velocity, more related to sounds from the pipes when you open taps, etc. And there's, of course, also a list of pipe diameters that are available, and the program will give you the proper pipe sizes. So here is a bit more specific for this apartment building. I got some figures here. On the right is a table. So in gallons per minute and liters per second, the type of or the flow rates per fixture, and also how we would calculate that into fixture units. And we also did the same thing for the flow rates that are more often used in the US. So the lowest one here, the lowest line, is the new ISO 55 Simdeum based prediction of maximum flow rates in a year. And even for 45 apartments is about 1.5 liters per second, or about 20 something gallons per minute. Now the old ISO 55 is the next line up, and that uses 25 fixture units, the Dutch fixture units. The one above that is 47 fixture units, which would be the ones if I use the UPC or the water demand calculator values. And then if I would use the IPC values, there was a bit of confusion on our side. Do we calculate all the individual fixture units and then take the sum of that and use that? That would be 106. Or do we look at the sum that IPC gives and convert that into fixture units, and then that would be 172. But you can see that there's about a factor 7 between our Dutch estimate and the flow rates that we would expect according to the IPC values. Now, how would that convert into the various pipe diameters? Instead of running it, a lot of times I decided to make it a bit more graphical like this. So the number of apartments with the given maximum flow velocities that we allow, and assuming that there is actually enough pressure available, you would see that in our new Dutch version, we would use typically a 4-inch, 5-inch, and a 6-inch pipe, and that's it. Whereas, according to the way we would design it with the IPC values, it would be 8-inch, 10, 12, and even 14-inch, which is not really used very often. Again, here is the number of the inches, the American values on the left, and diameters in millimeters on the right. What else? Well, if we were to use the old value for the Dutch way, we would also have 5-inch, 8-inch, and 10-inch. So that would already, I'm not looking at the wrong line, 5, 6, 8, not 10. So that would already be always one pipe size larger. So by having this newer, more realistic, because we also tested it against real measurements, you could go one pipe size down in copper, and you can see the same thing in plastic pipes. Well, thank you for listening. And again, thank you very much to Henk Jan for providing me with all the data.
Thanks very much, Miriam. Appreciate it. Our next speaker is Frank Schmidt, who is with Kemper in Germany, and he is going to present next. Frank.
Yes, here I am. Okay. Yeah, there we go. First slide of my presentation. The German pipe sizing design is specified in our DIN 1988 part 300. Part 300 doesn't mean that there are 300 parts of this document. There are only 6. Part 1, 100, 200, 300, 500, etc. to 600. And part 300 contains the pipe sizing method. As you can see, I've used a software for it. And the design principle is basically divided into 5 different steps, which I would like to introduce to you. They are basically not all completely different to the methods used in the Netherlands or in the US, which we will see later on. So on the next slide, we can see the beginning. It all starts with the determination of the design flow rates of every fixture. So that is one difference. We are not using fixture units. We are designing according to a real flow rate of a fixture. The standard, therefore, gives us a general number or general information about different types of fixtures, general outlets like a wash hand basin. You can see that in the table. They have a flow rate of 0.3, for example, in different circumstances, at a certain dynamic available pressure, because it makes a difference if you want to achieve 0.15 liters per second at an available pressure of 1 bar or only half a bar. So that's also different. So therefore, we always have to implement 2 figures. We have to implement a design flow rate at a certain minimum available pressure at the fixture. On the right, you can see a little schematic of a bathroom with 1 shower, 1 toilet, and a wash hand basin. And then you start at the very last end at the shower. If we follow the cold water line, which is the green one, then you see we have the last pipe to the shower that needs to supply 0.15 liters per second. If we add the toilet in the middle, which should have 0.13 liters per second, then we are at the 0.28 liters per second. And at the beginning, we are adding the wash hand basin with another 0.07 liters per second. So we need a total flow rate of 0.35 liters per second. We are just adding up the separate flow rates of every fixtures. There is an exception. We can also build something called usage unit, because that's going into the direction as what Dan told, that we're suggesting that not all fixtures in a typical bathroom will be used at the same time. So we can reduce this, and we can only take into account the two biggest outlets. In this case, it would be the toilet and the shower. And that goes into our simultaneous use conversion later on. So the second thing is then calculation of every pipe section's total design flow rate, as we just did. When we've done that on the third slide, then we come to the determination of the peak flow. So for every pipe section, we are adding up the different flow rates it has to supply to the fixtures. So we get a total design flow rate. And then we just use different functions to convert this total design flow rate into an estimated or a probably appearing peak flow rate. And this conversion takes into account the simultaneous use. These functions, you can see that we have 6 different functions. Basically, the linear function, this is just for information. Nobody would use it. Maybe in a stadium one day, if there is a big break during a basketball game, then everybody's going to toilet, then you can have the linear function. But usually we are using different functions for different types of buildings. And these functions have been created based on real measurements decades ago in Germany in the different building types. So you can see we have the lowest simultaneous use in a nursing home. The second one, the red one, that's the one I have used for our 45 apartment building, is the residential or for assisted living or elderly home. The third one is for school and administration building. And the two highest curves are for hospital and hotel. This covers or is a bit identical to what Dan also introduced, where he said that the Hunter's curve has different fixture units for private buildings and for public. So for public, the numbers are a bit higher, and public, I would say, is also hospital and hotel. After that, after the design or determination of the peak flow, we can see the next slide where we have the function. Unfortunately, I've done a little mistake here. The delta P loss is the remaining pressure. So that should be the determination of available pressure gradient for all flow paths. So we are basing the pipe sizing on an available pressure drop per meter. So millibar per meter. So how much pressure can we waste on every meter of pipe? This is calculated according to this function. We are taking into account the relative proportion of fitting losses as a start, and for private houses, for example. But for public buildings and for bigger buildings, we have to take into account not just a percentage or a relative proportion. We have to take into account the real figures of every fitting, and that's done with the losses of fittings in the detailed sizing method, and they are calculated based on a pressure drop gradient called zeta value. So that's the equation below, and that's why even in our design it is recommended that every design is done with a software rather than manually, because it's an iteration. So back to the above equation. So the available pressure is calculated by taking into account the relative proportion of the fitting losses times the remaining available pressure. The remaining available pressure is actually the pressure that is coming out of your booster set, or either if you have a direct fed system from the city streets main and you're coming in with, let's say, 80 psi or 5 bar, then this pressure is deducted by the pressure loss due to a water meter, a filter, the geodetic height, etc. So you're deducting this this pressure also by the minimum pressure that we require at the fitting that we've seen in the table on the second slide before. So if we need 1 bar at the toilet, that needs to be deducted as well. And then you end up with a available pressure that is to be wasted on pipe fit or pipe length. So then you get your R value millibar per meter. And taking this into account, then you do your pipe sizing, of course, with respect of maximum pipe velocities. They are different for copper or different material. We allow different flow rates, but the leading value is the pressure, available pressure gradient. So if we then go to the next slide, there we see our building. This is the 45 apartment building. The yellow marked flow path is the critical flow path. And we start with this flow path to set up, or that's the flow path that specifies my available pressure gradient at the beginning. And based on that result, I'm sizing my pipe work from the house inlet to the fixture at the end of the critical flow path. So that's determining my pipe size. And then, of course, yeah, as I said, the maximum allowable velocities have to be respected. And after that, I'm doing that for every flow path. So for this building, for example, we have in each apartment, we have 10 fixtures, 8 fixtures with hot and cold, and 2 fixtures with cold only. So we have a total of approximately 810 flow paths. So we have to redo the same work for 800 flow paths again. Approximately 810, I think. Yeah, that has the result that our pipe sizing does have different results than what Jeremy said, where he said that the pipe sizes in the apartment are basically identical, and then he copies it 45 times, and then he specifies the pipe sizes of the ceiling void distribution pipes in every floor, and also copies it from the 5th floor down to the 1st floor. So in our results, it looks a bit different that we can see on the next slide. I have made, that's what I said already. That is the effect that we have based on our design process. It's not identical everywhere. So this is a very simple graphic of our 45 apartment building. We have the 9 apartments per floor, and we've got the 5 floors. And there you see the floor distribution sizes. The change of the size, from DN40 to DN32 to DN25, it is shifted. So the closer you are to the water source or the pressure source, the more pressure per meter you can waste. And that has the effect that in the lower floors and nearer to the riser, you can size your pipes smaller, always with regards to the maximum velocities, of course. But that reduces the volume and reduces the waiting time for proper water temperatures, for example. So, and on the top, you see there we have DN40 in the 2nd, 3rd, and 4th floor. And on the 4th floor, the DN40 is reduced to DN32 just after the 3rd apartment. Rather than in the 2nd and 3rd apartment, we change to DN32 after the 1st apartment already. And in the first 2 floors, we don't even start with DN40. The same thing to the end. You can see the shift to 25 is earlier in the lower floors, and in the upper floors, the change to a lower distribution pipe is coming later on. The same thing or a similar thing appears in the supply pipes to the apartment. If we go to my last slide, there we see that in the entire 1st and 2nd floor, we have only apartment supplies with DN20, which is 3/4 inch. And in the 2nd floor, we have more or less 50%. 4 have the DN25 have 1 inch. And on the 3rd and 4th floor, we only have apartment supply pipes of 1 inch. So that's the basic effect of working with the pressure gradient. But that's basically the short introduction for the German way of design.
Thank you, Frank. Yep, we have one more presentation before the discussion. So Gary Klein is next, and he's with Gary Klein and Associates, and he's going to talk a little bit about the architectural choices that can impact premise plumbing systems.
Bill, you ready? Thank you. So I want to focus on how the architecture affects the decisions that are made by the plumbing engineer and the plumber. So let's just get started here. So this is looking at a single family detached and 1 unit in a 6-plex. This was part of work that was done by Stantec for IATMO as part of a recent project they did to look at the cost effectiveness of using the water demand calculator in new construction. And so these 2 units are the same size, about 2,400 square feet in each. The apartments don't get garages. They have, entries to the apartment. These are mirror images of each other effectively. What I want you to see is that there's some distances and some choices that have been made. So as the building gets bigger, the distance between the fixture groups gets larger, and that horizontal distance adds length and volume to the plumbing. And if we're concerned about things like residence time in a building, we need to keep the volume down in order to get turnover higher. So spreading things apart increases distance and volume. The second thing I want you to see is the water heaters closer to the fixtures. When the water heater on the left, it's closer to the fixtures because of where it's located in its mechanical closet. And on the opposite side, for the same floor plan, we decided to put the water heater in the far corner rather than in the near corner next to the fixtures. In order to do that, we would have had to relocate the door in the right-hand mechanical room, utility room. And so a single choice of where to put a door ends up affecting where you put a water heater, or vice versa. And that, again, it's extra distance and extra volume, and the pipe from the water heaters going toward the rest of the fixtures is larger diameter inside each apartment. And so again, it's a big lever on volume. Making those kinds of choices to put things closer together or farther apart has an impact. Next, please. Oh, this is lovely. This is showing the same 2 using home run manifolds, the central home run manifolds. And so I'm interested in the hot manifold because I'm concerned about the time to tap to get hot water to fixtures in question. And so, again, same floor plans. Someone chose to put this on as a diagram. In the case of the left-hand building, the single-family detached, the water heater is to the right, and the manifold is shown as further away from the fixtures. And because it's further away, you add volume to every single one of what I'll call the twigs that go to each fixture. It's, a couple, 3 feet, but you have to repeat it because you're going back and forth. So anyway, it adds feet, adding feet adds volume, adding volume adds residence time. And so we have to think about locations. On the other side, the manifold, the hot water manifold, is closer to the fixtures than the water heater. And it's in the right position relative to the fixtures. I'd still like to figure out how to move that water heater up to the upper right corner of its utility closet, but that requires moving a door. The other thing I would note is that in the second case, the 1 unit of a 6-plex, the manifold is on the far wall from all the fixtures, whereas on the single family detached, it's on the near wall to all the fixtures. Again, it's a set of choices that are made having to do with where you locate things. And those choices are often made by the architect, putting things in certain places that make it very difficult to do anything other than what's shown here by the plumber and the plumbing engineer. I think we have to get people to think more systematically and integrate more systematically about this. Next slide, please. So now we're going to look in the one unit in the 45 unit building that we're discussing today. These units are 1,000 square feet as opposed to 2,400 square feet. So much smaller, 40% as big, I think is roughly. And again, we can see some interesting choices. We have a relatively long, skinny utility room in the laundry room, and that makes perfect sense given the layout. We managed to put the water heater as far from the kitchen sink as one could possibly do it in this dwelling. And that has a fairly large number of feet to get from the water heater to the kitchen sink. Kitchen sinks are used a lot. That means that fixture, in my opinion, ought to be closer to the source of hot water than is shown here, because otherwise an awful lot of the hot water events that one drew at the kitchen sink will never arrive hot. Right? The pipe is longer than the volume of the event. So is there any way to rethink this laundry room and utility? And maybe it might require another door to make it work better. But these choices have an impact on the plumbing design. And then you've got the hot water manifold is now far from the water heater, and it's on the outside wall, and it's far from the fixtures. Why is this important? The pipe from the water heater to the manifold is large diameter, typically 3/4 or 1 inch pipe. And by putting it schematically far away from the water heater, you've added large diameter and volume to get from the water heater to the manifold. Ideally, the manifold would be very close to the water heater, as close as practical or as allowed by various rules. Again, it's on the outside wall of the apartment rather than the inside wall closer to the fixtures. All of these things have impacts on the volume and time to tap, as well as the volume in the whole plumbing system and residence time. Next slide, please. So a few comparisons, pulling out from the Stantec report and looking at the largest diameter pipe in each of the calculations they provided for the 45 unit apartment building. The International Plumbing Code in the apartment came up with 1 inch pipe. So did the Uniform Plumbing Code. The water demand calculator for cold water entering the apartment, this is all cold water enters the apartment, is 3/4 inch. Again, because of each of the has different perceptions on the flow rate at peak based on the method of arriving at the answer for flow rate. And then the hot water pipe sizes are about 3/4 or 1 inch in the apartment for the IPC and the UPC. But in the water demand calculator method, the maximum size is 3/4 inch. Next slide, please. And this is showing at the 45 unit building level, the whole building, the differences in peak flow rate for the 3 different methods that were evaluated in the Stantec report. And we're using this Stantec report's model of the building for this discussion today. And so it's a big difference in peak flow rate or liters in gallons per minute or liters per second. Not, what is it, almost 7 times on the biggest difference. That's a huge difference in expected peak. And as Miriam pointed out, and Frank pointed out, if you've got measured data and you're not using it, we're fooling ourselves. We have huge extra volumes in the plumbing systems based on the current methods that are most commonly used here in the US. The next slide, please. And again, click. So what reduces residence time? For a given flow rate, residence time is due to the volume in the system. Next. So what reduces the volume? Length and diameter, reducing the number of fixtures, architecture that clusters fixtures and appliances close to each other, right sizing, the premise plumbing and the water heaters and other components. What I want to talk about for a minute here under what reduces volume is the number of fixtures. In the UPC and the IPC, and I am assuming in the National Standard Plumbing Code, I haven't read it, but I'm assuming it's there is a requirement for a minimum number of fixtures for each occupancy. For hospitals, the Facilities Guideline Institute has a similar set of minimum requirements for healthcare facilities. Well, an awful lot of fixtures in an awful lot of buildings are underutilized rather a lot. I realize that's crazy, but it's true. And so I think we actually have to think hard about the requirements for minimum numbers of fixtures based on data we have about usage. Maybe we don't need to have 14 sinks in a bathroom, a public restroom. Maybe we only need to have 10 or 6 or something like that. And still with the queuing would be fine, and the use would be fine, and there would be very little problem, right? But every fixture ends up with what I call a twig, and every twig is connected to a branch, and every one of those twigs is spending an awful lot of time in the stagnant condition. Not simultaneous use, 0 is the most normal condition. And that has a lot to do with the resident's time in the plumbing and whether or not that twig has the potential for helping to grow more pathogens. The third part here is how do we future-proof the plumbing in new buildings? Flow rates are going down, at least as far as I can tell. I don't see them going back up. And so if that's true, we should be thinking really hard about the impact of the plumbing going into the building, because it's going to be there for the life of the building, pretty much. 50, 60, 80 years, even if we change it out, we rarely change out plumbing just because. We change it out when we're doing a major renovation or something failed. I think we need to plan our plumbing systems for strategic flushing. Right now, an awful lot of plumbing appears willy-nilly. It goes wherever, it's connected in whatever way makes some sense to whoever's doing the work. But I think we need to think about pathways that are sort of like the critical path that was described in the plumbing design, right? That pathway should be a flushable point at the end of the path so that you know you flush that route. And I think we should think similarly about other pathways in the plumbing in the building. The more complicated the plumbing, the harder it is to think about the strategic flushing. And personally, I think we ought to label the endpoints so we know where to flush. That would make it much more effective and quicker to do that when we choose to do flushing of buildings if we need to do it. And I suspect we're going to need to do it. And the third point here is that an idea that occurred to me during this developing this presentation is that if you have a large percent of the plumbing in the critical path compared to the total plumbing in each zone, you have less total feet of pipe. It's keeping the twigs and branches off of the trunk on the critical path small, and that has to do with the architecture. And so I think we ought to be looking at that in order to create more efficient plumbing systems with less total water in them. I think that's it. Thank you.
Thank you so much, Gary. I'd like to ask all of the speakers to turn their cameras back on, please. And in the next section of the webinar, we are going to talk about the results of the pipe sizing approaches that we've just discussed. So we'll show some slides, and we'll ask some questions to try to help clarify why each of these design approaches results in such different results. So if you have questions, please put those into the chat, and we'll try to ask those as we're going along as well. And again, we'll probably have about 30 minutes just for kind of a panel discussion, open discussion, and comparison of the results. And then we'll move into our final speaker at that point. Bill, could you please put up the first slide? Great. So this slide is showing some of the input assumptions for each of the different approaches. Let me just walk through the top of the screen. The top of the table shows all the different design approaches that we've talked through today. So we have for the US, the IPC, the UPC, and the water demand calculator approaches. For the Netherlands, we have the old ISSO 55 and the new version. and then we have the Germany approaches as well. And then along the different rows of this table, we're showing each of the different fixtures that's in the apartment, and then our input data about what the fixture unit values are or the flow rates associated with those. And you'll see for a couple of the methods, we don't have a value, for example, because that method, for example, with the Germany method, they don't use fixture units, so there's no value there, and vice versa for some of the cases. So just to start, I'm going to ask Dan a question. Dan, if you could turn your camera back on and join us. So Dan, you showed very nicely in your presentation that the flow rates can be very different, and the fixture units between the UPC and IPC methods. I wondered if you could explain a little bit more, provide some insight into why those numbers are so different between those methods.
I don't know if why my camera's not working. It's on. It just does not like me today, I guess. But anyways, so the question is, why are the fixture unit values different between the UPC and IPC? Starting with the original Hunter's curve, the curves do not have the origin at 0 because it's a probability curve. You have to have so many number of fixtures to begin with to have at least 2 operating simultaneously. So, for example, I think the flush valve curve starts at the fixture unit of 60. So all Hunter did was extrapolate 60 all the way down to the lowest fixture unit value, which was 4. The IPC extrapolated it differently. I don't know their reason why, but they departed from the original Hunter's curve and they extrapolated differently. So on the low end, where you have the individual fixture units, you're going to see these differences. But when you compare the flow rate, when you go to the conversion charts of each code, then the IPC's flow rate in many instances are higher than the UPC flow rate. But there's a difference in the way that they extrapolated the curve on the low end.
Great, thank you. I appreciate that. And I think there's a question for you in the chat, Dan. If you can see that, maybe you can comment on that. Great. Another question I have, and this maybe could be for Frank. One thing I'm wondering about with this chart is the different types of fixtures that might be used in Germany versus the U.S. Are those differences in the types of fixtures that are available that you purchase? Is that reflected in this chart as well?
Yeah, I think there are more than one factor. Of course, I guess we are using different fixtures, so different manufacturers with different numbers. As I said, our numbers are based on, usually we should use the designer's information of a certain flow rate of a certain fixture at an available pressure at this fixture. And I'm not too sure if in this table, if we need to look into more detail, if the US numbers or the Dutch numbers, if they are based on the same available pressure at the particular outlet. So that might be also a difference.
So Regan, if you look at this is Gary, if you look at the footnotes, we found in our conversations that in the US, we connect dishwashers to hot, and in Europe, they connect them to cold. And clothes washers in the US have both hot and cold, and in Europe, they have cold. So that impacts the sizing on either side of the plumbing system. That's another interesting feature of the differences. And I am very confused personally about where we mean the critical pressures to be. And in the US, our fixture flow rates, our faucets and shower flow rates, are rated at 60 psi for faucets and 80 psi for showers. And given that the plumbing codes state that we're supposed to have a starting pressure no greater than 80 psi, I'm really confused how we're going to get anything close to that at any of the fixtures. Frank's shaking his head, but the answer is can't. There's always a drop in the plumbing system somewhere, right? And so we're starting out at a deficit to begin with based on the way we rate the performance of things. Anyway.
Yeah, for example, here the standard value for the supply for the mains pressure from the street is up to 5 bar, and then you get a figure of a required available pressure at a toilet cistern of half a bar. So you can waste 4.5 bar on filter, water meter, and everything else in the system until you reach the fixture.
Right. We have similar numbers for the US of residual pressures at certain fixtures. And I remember in our work that you had a critical path to the kitchen sink, and Jeremy doing the math in the US had a critical path to the showers. And it's likely because our shower valves have a higher residual pressure requirement than the sinks do. Again, all of these different choices affect our plumbing decisions.
For example, Gary, what you said, when the showers are rated at 80 psi, I think that's approximately half a bar. So that's where we are starting with. Shower is usually at 1 bar, so double.
Okay.
If I have converted correctly here.
I'm not certain of that. I thought a bar was 14.
Oh,
anyway,
yeah. Yes.
I don't know.
Okay.
So it doesn't matter, but the point is that we have different decisions made in different places, yet the physics ought to be the same everywhere. So anyway, I think it's interesting. We should move on. There's some other good stuff here.
Yeah, so this particular slide is just highlighting the differences for the bath where there's a combination tub and shower. And so across the different design approaches here, you can see that the flow rate varies from, looks like a minimum of 2.4 in the Germany method up to a maximum of about 5.5 in the water demand calculator. Wonder if folks from the panel could maybe jump in and help to just talk about reasons why we're seeing such a wide range of values.
Well, I could speak for the water demand calculator. We had a database of residential end use of water surveys, over 1,000 homes. And from that database, we were taking a look at the bathtub flows, and 5.5 gallons per minute was, I don't know the exact number, but it was above the median value. We did not want a flow rate too low coming out of the tub filler, where the occupant would have to wait an awful long time to fill a bathtub. But we also did not want the flows to be excessive. So 5.5 is close to the median of all the data of end flow uses from bathtubs. But you could go lower. I kind of did a poll around my office on what people would consider satisfactory time for filling a bathtub. How long are you willing to wait? If you start dropping below 5 to 4 gallons per minute, you're not going to have customer satisfaction for the time that it will take to fill a bathtub. So, but like I said earlier in my presentation, you can go lower than 5. You can put an input lower than 5.5 gallons per minute if you want to design a flow rate less than that for a bathtub.
So Dan, this is Gary. I've measured the flow rates coming out of combination tub shower valves, the ones that are ASSE 1016 protected for anti-scald, which is the modern tub shower valve in the US. And quite frankly, if you have 5.5 gallons per minute, I think the numbers are a pressure drop through the valve of about 45 or 50 PSI. And given that we're starting not much above that, I doubt we're going to see that much flow rate coming out of the tub shower valves today. if you have a standard standalone tub with without the anti-scald protection inside the valve set, there's much less pressure drop. It's a hole, right? And you'll get higher flow rates. But the combination tub shower valves that I'm seeing we're using today, we won't see that high a flow. The other point I would like to make is that if we're designing the hot side or the cold side, the combination tub shower valves that we have today in the US don't allow full flow on either hot or cold. And so if we're designing using the water demand calculator to design the plumbing for the hot or the cold, we should be able to discount the peak value by some amount. That range for the valves I measured is 60 to 80%. So 0.75 is right in the ballpark. You could put 0.8 in so that you have some of the safety factor. But anyway, I think that there's some interesting features about how to use the water demand calculator based on real measurements of those shower valves that we ought to be using as we go forward.
There's one question for the chat that is asking about the peak demands. So we're making some assumption about peak demand flows, but what is the period that we're assuming for how long you're at that flow? So is it for a few seconds or some other duration, or does that vary by approach?
Speaking again for the water demand calculator, when we're estimating the 99th percentile, that's at an instant of observation. To derive the probability values for each of the fixtures, we did go through the database and we did pick the peak hour to determine a representative p-value wherever that peak hour occurred. It could occur in the morning, it could occur at night, it could occur in the middle of the day. Wherever that peak hour occurred, then we weighted those p-values to determine a representative value. But the 99th percentile peak demand is at an instant of observation.
Miriam, you have a good point. How big is a bathtub? and I don't think that, I think that that's a pretty typical bathtub here in the US too, certainly for tub shower combinations. Ron George points out that some tub filler spouts can be up to 12 gallons a minute, and that's true. I actually saw an installation of one of those very large garden tubs in a home some years ago with 3/8 tubing connecting it, and they were wondering why the water came out of the tub filler at such a dribble. Well, it had no choice. It had this great resistor in between the tub and its trunk line. So it took a really long time to fill this really, really big tub. I have no idea why the plumber put that in. Can't figure that out at all.
Bill, let's go to the next slide. So this one is just highlighting the master bath and showing the differences, but yeah, we can go on to the next one, Bill. Thank you. Great, so this slide is showing the output of the pipe sizing methods for each of the different methods along the rows of the table. And then the green boxes are showing if we made the assumption that the building riser was in the center of the building, like in the picture we showed earlier. Or in the orange section, it's assuming that the riser for the building is at the far end of the building, and so it's changing the architecture in some sense there. So so all of these different columns are showing some of the results of the different methods. So Bill, the next slide I think focuses in on just what is the pipe size at the entry to the building. And so here you can see again the output of these methods, which is telling us what pipe size to use in different locations. Here it's at the entry to the building, and here we're seeing some differences. So would any of the panelists like to jump in and talk about why the methods are giving different results? And then we'll start talking maybe about the implications of this.
I'll go ahead and start off since IPC is at the top there. So IPC sizing was done without taking any additional diversities outside of the Hunter's curve or the IPC table in the appendix that tells you with this fixture unit you have this GPM. Nothing was diversified any further than just the fixture units using, pretty close to the old Hunter's curve. So that's why the sizing is as much larger than the water demand calculator, which we know is closer to reality.
And then speaking about the UPC, the only difference, both the IPC and UPC uses the Hunter's curve. So the only difference is the difference in the fixture unit values themselves that determined the pipe size.
And Frank,
Yeah.
looking at the two choices there, they ended up with the same. That was really odd to me.
Yeah, I think that shows. I mean, the second version, Germany, US WDC flow rates. That's the water demand calculator flow rates. I think they have been the lowest values from the three different US versions. The three lowest from IPC, UPC, and water demand calculator, and they have been closer to the German values as the other two. And it also shows me the big impact of the simultaneous use function. And that's why we ended up with the same sizes, regardless if I take the German design flow rates for the fixtures, or if I use the converted fixture units into design flow rates and put them into the software. So everything else remained identical, the pipe length, the geometry, insulation, everything, pressures. So that are the two only differences.
We have a question from the chat that says, who establishes the maximum velocity constraint? Is it based on pipe material and size?
Question to me?
Any of the panelists could answer that.
Well, yeah, it is a lot to do with the pipe material. The Copper Development Association, they are the ones that recommend the maximum velocity for hot and cold water, and even lower for a recirculating system. The PEX people, I know Uponor, I think they allow 10 feet per second on a cold and 8 feet per second on a hot. So it does depend on the type of material. And also the noise factor, like Miriam pointed out, that has a factor in it too, water handling.
Yeah. And I think another factor that we are using is what kind of pipe is it? So if you have a cold water or a hot water distribution pipe, it is more likely that there is lower or less flow, because you will not always have the peak flow rate in this distribution pipes. So we allow a higher flow rate in the supply pipes than in the circulation pipes, for example. In hot water circulation, we are limiting the velocity more than in the supply pipes.
Great, let's go to the next slide, Bill. So this particular highlight here is showing the calculated volume of the pipes that are on the critical path, as I think Jeremy showed that nicely in his pictures earlier. And here, so you can see that the total volume of water in this critical path is quite different in these approaches, varying from 6 from the water demand calculator to 27 about from the UPC method. We also heard that the pipe volume can have lots of implications. So does anybody want to talk about what the implications are of having a lot of pipe volume, a lot of water volume in your system?
I could talk to this a little bit. So as you're looking at the pipe volumes, you got 22 gallons on the IPC side. So what that means to the end user on the most remote apartment building in this 45 apartment complex is, if no one else uses water, they need to flow 22 gallons of water in their apartment in order to get fresh water from the street to their dwelling unit. So, obviously, the lower the number, the more likely you are to have fresh water sooner Obviously, if out of 45 apartments, more people are going to be using water. So, it's not 22 gallons for just that unit, but that's the extreme case of, you're the first person in the building and no one else moves in for 6 months. You got to drain 22 gallons to get your water to turn over to fresh water from the street.
Actually, Jeremy, it's probably worse than that because it takes more volume for it to actually fully turn over, but it's a minimum of the volume in the pipe.
Yeah, these are just numbers going up to the apartment. This isn't counting what's inside your apartment, what's inside your water heater.
Right.
It's just in order to get it to your front door, that's what you have to flow.
So that's something that we agreed not to calculate, the water heater, in our discussion for this week because it complicates matters. But the volume in the water heater is large relative to the volume in the piping. If you have a storage water heater, even a small one is 30, 40 gallons. Most are 50 today in the US for apartments or dwellings with this many fixtures in them. And that's way more than the volume of the plumbing in the apartments. And so the hot side has much more residence time than the cold side does, doesn't it?
Absolutely.
So, Frank, I'm looking at the comparisons and the numbers. The German method is about half of the US.
Mm-hmm.
And then the water demand calculator is half of the German method. In volume on the critical flow path.
Yep, that's true. So that's the pipe work up to the front door of each apartment.
Yeah.
Could that be?
Reagan, can you go to the next slide? Because I think it's going to show the far end. So Miriam, your numbers are in the middle of all that too.
Yeah.
Pipe size.
So our new approach, the ISO 55, the top one there, is quite similar to the water demand calculator,
Yes.
which is nice. And the older one is very close to the German, apparently. And I think we didn't use the numbers for the water demand calculator, but the IPC values. So, and those are similar in the result as well. So,
right.
I think that went
yeah, what's interesting is if you look in the gray side, we don't have a slide to move to it, but if we look over to the right in the gallons per minute, just stay with the slide we were on. Oh, good. There we go. So I'm in, yes, that column. I'm looking to the right of that column, which we can sort of see. The water demand calculator is the same diameter as the Netherlands ISO 55, but look to the next column and you can see that the maximum flow rates are different and yet the velocities are similar, right? It's very interesting to me to see that. Each of our methods has enough differences that we're still not quite at the sort of the root of the issues yet, but we're getting close. I think this has been a very useful exercise to better understand how the different methods impact the choices.
So on this slide, we're comparing, again, the location of the risers either in the center part of the building or the far end. I wonder if we want to talk a little bit here about any of the implications for water quality in the building. We can talk about this here, but also in the next couple of slides as well.
Let's go to the next slide because I think it opens up to the last
Sure.
Look at the far column, the central versus far end. The choice of where we bring the water into the mechanical room makes a difference, doesn't it? And it's a rather large difference on the critical path.
Yeah,
as soon
as we put the riser in the middle, we just cut the critical path and all the other flow path into half, more or less. So for the German desizing, that makes a big difference because when we are sizing with regards to the available specific pressure loss per meter, that makes a big difference. So we can allow to waste more pressure per length of pipe.
Right.
And therefore design smaller.
So, Jeremy, we don't do it that way. We decided that to basically take each apartment and plunk it down and say that the branch off of it is the same. And Frank's method didn't do it that way, right?
Yeah, so you can see where his numbers are much lower on the building central than what we have in the IPC, and they're pretty similar on the far end, IPC versus his numbers. So by him doing it, you're losing more pressure, so his pipes are getting larger, and they're incrementing. As you get further away, they're getting larger, right? Or needing to get larger to overcome the pressure loss. So that's where his volumes, it really starts to blow up, and it really underscores the extra pipe volume that's added just by simply moving the riser to one side of the building, which we kind of joked a little bit that a pipe service line in the middle of a building in prime real estate area isn't likely to happen. It's more likely to be on the backside or a side of a building to free up that high value real estate for the apartment complex to utilize it a little bit better than just having a mechanical room.
And another fact is, if talking about water hygiene and water comfort and temperatures, so if you want to have proper cold water temperatures, having the riser in the middle is also very beneficial, because the water has to travel a smaller distance, shorter distance from the building inlet to the critical path fixture, and therefore you get the cold temperature very fast instead of having the water traveling through the entire building. And another thing is that also by traveling through the building, due to all the good proper energy saving codes nowadays, we have in the meantime warmer and warmer shafts. And therefore we also assume, or we recommend, to separate hot and cold water pipes in two different shafts, so that the cold water temperature increase by picking up the environmental temperature is decreased. And this is also critical to the distance the water travels through the building.
I like that idea a lot, of separating the cold and the hot plumbing pathways. I think it makes a lot of sense from an energy perspective as well as the health and safety perspective. Hots with hot, colds with cold, never the twain shall meet until you get to a fixture.
Yeah, basically you don't want to chill your ceiling void down by cold water.
Yeah. I'm also worried about running hot or cold pipes through HVAC plenums, which is allowed. And I think we ought to revisit that allowance. Cool. We should move on. We're getting close here.
Yeah, we have about 5 more minutes, so I'm going to go to the last slide.
Okay, great. Yeah, we just got a couple more minutes left for discussion. So if anyone has any other questions, please go ahead and put them in the chat. We'll try to get those answered, and then we'll move to our final presentation. So this slide is showing the comparison of the different pipe sizing methods within the apartment. So the first column is showing the pipe size at the entry to the apartment rather than the entry to the building, which was on the other slides. Let's see. So here again, we see similar differences between the methods. I'm wondering here if we also want to start talking about just what are the implications of all these different designs on impacts to things like water quality, pathogens and microbial growth in the building, energy usage. Anyone want to jump in on that question?
Less is more. Everything with large volume has extra costs, if you will, in terms of water quality, you've got to clear out more water, as Jeremy pointed out. Well, from the entry to the apartment and then in the apartment. And so you lose energy whenever the hot water lines cool down. If there's more volume, more energy is lost at the end of the event that has to then be replaced at the beginning of the next. Bigger diameter pipes, correct me if I'm wrong, the velocity is slower, so probably more things drop out of solution and settle to the bottom of whatever's horizontal. What else is there?
Yeah, I mean, you touched on the larger diameter is a slower flow rate. So if you're thinking about the actual flow rate, what's really happening, yeah, in a larger pipe, it's going to be a lower velocity. So we pushed the 8 feet per second for cold and 5 feet per second for hot, for what copper recommends, but also the higher the velocity we can get, the more likely we are to scour that pipe. And keep it clean of biofilms, which can seed on the side of the pipe and breed the bacteria and waterborne pathogens that we know is a reality in our world. With oversized pipes that we see all the time. We always, I joked before, we've always had the moniker, no one ever complained about having too much water pressure or too much hot water. But now we know that, this oversized idea of piping is wrong because it has the side effect of the bacteria and waterborne pathogen, breeding in that. So, what we try to do is just skinny the pipe and be a little more aggressive on the sizing to get it closer to reality flow rates versus, code and Hunter's curve.
And to piggyback on what Jeremy said, I'm wondering about the chlorine decay in larger pipes where there's more stagnation. What chlorine residual? And I know I don't believe the Netherlands uses chlorine for disinfectant. The U.S. does, and the U.S. does require a chlorine residual at the tap. And I just wonder what effect larger volume. Oversized pipe, larger volume water, what effect that has on the chlorine residual.
Yeah, it's very much a cascading effect because you have slower flow rates, so you have biofilm. The biofilm is getting attacked by the chlorine, so the chlorine attacks something and it's done. It doesn't just attack something and move on to attack the next thing. So it's dropping the residual as it goes through the building. So, the larger the pipe, the less likely you are to get enough chlorine at that tap. The most remote branch of your building isn't going to get the same amount of chlorine as the very first fixture off the main coming into the building. So, yeah, the larger the pipe, the less likely you are to get good chlorine within your building.
Great. I want to give Miriam an opportunity to add to this conversation, but also ask her our final question for the group today, which is related to using hydraulic models in the future. So, Miriam, I'm wondering if you see other types of data or information or methods that would be useful in improving these design approaches, and how might you think hydraulic models could be beneficial in that area?
Thank you. Well, one to add to how bad is it if you oversize pipes, I think, well, we've done some temperature modeling. We also saw the water in the pipes getting warmer and cooler and warmer and cooler depending on flowing or stagnation, and the temperature that could be different in the risers or in the horizontal sides, and you just don't know what's happening at all, and that could affect all sorts of biofilm related, even with or without chlorine residual. One nice thing that could bring hydraulic modeling and design together is to answer a bit of that question I think Steve Buchberger asked: how often do these design flows actually occur? So once you've designed your system, you could run hydraulic models and find out how often it does occur and how often you potentially could have a too large velocity, too large pressure drop. Probably this gives extra room for going to a little bit smaller pipes even. And another thing that we definitely found out while doing this exercise is that it would be very, very useful to have some standard models for different types of buildings that we could also use in hydraulic modeling, because there's just this subtle differences, and you never really know how to explain things unless you use the same basis. So I think that would be nice.
Thank you.
Miriam, you reminded me of something else about the design that we started with. Each of the apartments had its entrance far away from the water, far away from the entrance to the next apartment. The apartments weren't mirrored, they were separated. And that choice affects the total volume of plumbing in the building. And we ought to be looking at designs that of our standardized models that minimize the volumes or maximize them, so we know what we're stressing when we do the hydraulic modeling.
All right, Bill, you want to jump into your talk here?
So in doing all of this conversation was very wide-ranging, and I wanted to sort of try and wrap up and put some closing thoughts on everything we as a group have talked about over the last month or so. So I'm just going to sort of summarize where hydraulic and water quality modeling is going to fit into the discussion that we had today. So as Regan introduced at the beginning, the sizing is done around fixture units or some sort of fixture rating. You get the size, peak flow, velocity to get the design. And then for water quality, water hydraulics, we use the water use, the demand, what's the flow, the actual flow, the pressure, what's the energy use, the water quality. And so we need to bridge the gap between going from the design and then having all this additional information that we can get from more advanced modeling techniques. So the hydraulic modeling, it can do a lot of comparative analysis, analyzing different scenarios of the building, the physical parts of the building itself for what the impact on hydraulics and water quality is going to be. So demand patterns, the use case of the building, the occupancy rates. In this case, we used an apartment building. It's sort of always going to be an apartment building, but you might just have like a strip mall or something like that might have varying uses within each of the units over time as businesses come and go. Different options for designs, different floor plans, plumbing layouts. Modeling can look at and do analysis on those. Operations in the building, hot water balancing, how often the building is flushed out for various reasons. The modeling can help inform a lot of that. And then long-term scenarios, as the building changes over time, the components decay, maybe there's upgrades, different fixtures installed, different components installed, major remodels, maybe a portion of the building is remodeled and not the whole thing. And then long-term energy usage in the building, and then finally just resilience to failure. I think the happenings in Texas the last couple of weeks has shown just how maybe fragile the water is inside of a building, and so resilience to physical damage, power failure, different contamination scenarios. These are all things where water quality and hydraulic modeling can have an impact. And so in what we've discussed today, these sort of fit into three different areas that were discussed. And the first is the plumbing design, what the plumbing engineer is going to lay out and will hopefully be constructed. They have to comply with the plumbing codes, but there's still a lot of decisions that have to be made. A couple of quick examples are the configuration. On a small scale, is it trunk and branch or a manifold system? At a large scale, where do the risers go? Is there single, multiple risers? Does it go in the center of the building or at the ends? And then the hot water is there a central hot water circulation system, or is, like this apartment, is there individual hot water units? And then plumbing material. We showed some differences between copper and PEX in the tables that we showed today, and that'll affect the water quality and the hydraulics. These are just some figures from today showing the different layouts and what these might look like in practice if you were to compare them. The riser being in the center here, or moving it down to along the side, or maybe supplying multiple risers up to each of the columns of the apartments. And then there's some things that are more on the like practical side, like design conventions. We pointed out dishwashers and washing machines use hot water in the United States, but is it actually hot when it gets there, or is it just cold hot water that's sat there and chilled back down to room temperature? Operations after occupancy, I mentioned the hot water balancing, but also water management programs, identifying those fixtures that are most vulnerable places that you might want to have monitoring at. And then I mentioned a bunch of changing conditions earlier already. And then the second area is the architectural design. Gary pretty much covered this, but what is the design of the building that we can reduce the water volume in the system and have better water quality in the building? Analyze the different uses, occupancy rates, as I mentioned, and then optimize the space in the building for the plumbing systems. Do we need pressure reducing valves on every floor? Can we optimize how those are used? And that also plays into how the building is operated. And then just to wrap up, finally, how can we inform codes and standards? That's the third area where modeling can have an impact. Hunter's curve changes that are being looked at, water demand calculator, and the Syndium stuff that Miriam touched on and informed the Netherlands codes. Those are great examples of how modeling has impacted the codes and standards in different countries. And then also looking at how to compare the codes across countries. This was a very complicated process to try and get a common language to show what different countries would do across the different methods. And modeling might be a good way to bridge that gap and find out what's done the best, what are the constraints, and maybe come up with a better way to do it overall. But code changes take a long time, so that's going to be the longest term change to implement from all of this. So, and with that, we are beyond our time, but I did want to wrap up as we usually do. If you're interested in joining the group here, please contact Joonsuk and join our mailing list. He did want me to note we, as the task committee, sent out a survey to better inform what we do moving forward with everything. So please look for an email from Google Form from Joonsuk and fill that out for us. And then next month we have our next webinar in March. It'll be on information management and modeling of premise plumbing systems. It'll be the last week of March. This is incorrect. Yeah, the week of March 22nd. Sorry, it's still the last week in March. But the final date is still to be determined. So with that, Regan, if you want to close out.
Sure. I just really wanted to thank all the panelists and speakers today. They put a lot of work into this project over the last few months, but I think it turned out great and was really interesting. I also want to thank all of you for participating and for sharing comments and ideas in the chat box. So I think there's a lot of area for future research and modeling work in this area. So I think your comments will help inform that as we go forward. So thanks again very much. Really appreciate it. And we'll look forward to seeing you for the next webinar next month. Thank you. Take care, everybody.